All right, hello Algebra 2. This is Notes Lesson 5.1, and we are looking at simplifying radicals. This is an entire unit on some mechanical things that we need to learn so that we can move on back to solving quadratics. So we need some extra skills. So we're going to be working with radicals and, coming soon, imaginary numbers. And then that's going to help us solve all kinds of equations. So you have IXL skill M9. And the first thing we want to do is make sure that we know all of these perfect squares. And so hopefully you know most of these. These are definitely numbers that you should memorize. So 2 squared means 2 times 2. Just thinking about what a power means. An exponent says repeat the base, in this case 2 times. So 3 squared would mean 3 times 3, and 4 squared would mean 4 times 4, and so on and so forth. And we just need to remember that. I think remembering what the exponents really mean goes a long way. So of course 2 times 2 is 4, and 3 squared is 9, and 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, and then 13 squared is 169, which are all perfect squares. So all of these purple numbers are perfect squares, and they are definitely numbers we need to know in order to take square roots, because guess what? A square root undoes a square. The square root of 10 squared, the square root and the square cancel out, leaving 10. They undo one another. So the square root of something squared just cancels out. That's really kind of cool. The square root of 5 squared leaves 5 because the root and the power cancel each other out. You should also know that a square root is called a square root because it has a little 2 right here in the elbow of the radical. It's an invisible 2. We don't usually write it. And that is called the index. Later on, we'll do equations where we have cube roots and fourth roots and fifth roots instead of just square roots. So anytime you see a square root, it's got a little number 2 in that index, and it's really handy if we're taking square roots, really handy if we know our perfect squares. So these are things you definitely want to keep handy. All right, let's do some simplifying. So example 1, remember you are supposed to be writing down the examples. I reference everything using these, and the directions, very important. This here is the product rule of radicals. So it looks like we can multiply radicals together. A and B just represent numbers. And we can multiply. If they're both radicals, then we can put them together under a giant radical, okay? And that's really important. You can multiply radical numbers together. So what we want to do is the reverse of that. I have a giant radical number here, and I want to break it apart. So we have radical 500. And radical 500 breaks apart into the product of 2 radicals. And I'm going to choose some very specific numbers. 500 breaks apart a lot of different ways. I could do 50 times 10, but that's actually not a good choice because there is a large perfect square. In fact, 5 times 100 would be a great choice because this is a lovely perfect square. So I'm going to write this as the square root of 100 times the square root of 5. And the reason I chose 100 is because that is a perfect square. And in fact, it is a very large perfect square, the biggest one I can find. And if I know that 100 is, well, 10 squared, so 100 is the same as 10 squared. And if I just told you, hey, the square root and the square cancel each other out, well, what is the square root of 100? The root is 10. The square root of 100 is 10. So it goes back right here. So if we take the square root of 100, we go back to whatever the base is, the root. The square root of 121, we go back to the root of 11. The square root of 144, we go back to the root of 12. All right, so the square root of 100 is 10. And then I can't do anything with this. It doesn't have a nice little root there, it's not a perfect square, so it just stays. So 10 radical 5 is the lovely exact answer. And it's fully simplified. Let's think about 24. I want to break apart radical 24. So we say radical 24 using perfect squares. 24 has lots of choices. It could be 8 times 3, 12 times 2, but I want to use perfect squares. So I want to use one of these purple numbers, and 4 is a good choice. So the square root of 4 times the square root of 6 is the square root of 24. Well then, what is the square root of 4? What is the root of 4? The root of 4 becomes 2. And then square root of 6 doesn't break apart anymore. And that's a great answer. We say 2 radical 6. And you should know this is 2 times radical 6. This is 10 times radical 5. When there's no sign in between, it is a product. It was a product here, and it remains a product. Okay. Radical 18, again, we want to break it apart. We've got some choices. We could say, hey, 6 times 3 or 9 times 2. Which is the best choice? 9 times 2, because 9 is a perfect square. So this is the square root of 9 times the square root of 2. And what is the square root of 9? The root is 3, because 3 squared is 9. So 3 is the root. And I can't do anything with the radical 2. It is not one of those lovely purple numbers. Okay, so that is the basics of simplifying radicals. This is stuff you absolutely should have done in Algebra 1. My problem is I don't actually know if you did it. So hopefully you did. We're going to do some more, but we're going to combine it with some other stuff. So here we have example 2. We are simplifying first, and then adding or subtracting like radicals. And I'm going to add that word in here, add or subtract like radicals, because it's very important that the radicals be the same, all right? Like terms, 3x plus 2x is 5x. These are like terms. Well, I also have radicals. 3 radical 5 plus 2 radical 5 equals 5 radical 5s. How about that? That's kind of cool. These are like radicals. They both have a radical 5, and so they are like terms, and we can add them together. Okay, so really, really important. So here, it's important you see here we have a coefficient of -2 with a radical 5. And here I have a negative, what I can put in a 1 radical 5. So these are like radicals because they both have the radical 5. And then all I have to do is combine the numbers in front, the coefficients. So -2 and a -1 make -3 radical 5s. You'll notice that radical 5 part doesn't change. We have, well, imagine 3 of them. Well, -3 of them. And that's our final answer. Okay, so these are like radicals. Letter B here. Are these like radicals? No, they are not. This one needs to be simplified first. So I'm going to do that. 12 breaks apart. I'm going to do it just below here. Again, thinking about perfect squares, I could choose 6 times 2, 12 times 1, or 3 times 4. What's a good choice? The 3 and the 4, because that 4 is a lovely perfect square. So this is radical 4 times radical 3. What is the square root of 4? 2. So radical 12 turns into 2 radical 3, but we also have the 6 in front. This is 6 times the radical. So we're going to bring that 6 down as well. So it becomes 6 times 2 radical 3. Well, and 6 times 2 is 12. So 12 radical 3 is what that term simplifies to. And now I can add it to the 6 radical 3. They both have the radical 3 on there. And so now all I have to do is combine the numbers. So 6 radical 3's plus 12 radical 3's is 18 radical 3's. And I like to say it that way. For some reason, I think it helps. 6 radical 3's plus 12 radical 3's equals 18 radical 3's. All right, same idea over here. These are not like radicals right now. This looks like just a negative radical 2. You can remember that's really, there's that 1 in there, negative 1 radical 2, which I think is helpful. So we need to simplify this radical 18. And again, 6 times 3, not a good choice. 9 times 2 is much better. So radical 9 times radical 2 is the same as radical 18. So you can kind of cross that out. And then, well, what is the square root of 9? Well, the square root of 9 is 3. So radical, whoops, that should be radical 2. So radical 18 changes into 3 radical 2. Don't forget about this 3 in front. This is a negative 3 times the radical, so it's negative 3 times 3 radical 2. Well, negative 3 times 3 is negative 9 radical 2 minus, I can bring this guy down, 1 radical 2 now. All right, so we have to do some simplifying first. Simplify first. Then you can add or subtract like radicals. All right, so now we've got negative 9 radical 2's minus 1 radical 2. All right, what's that give us? Negative 9 and a negative 1 make negative 10 radical 2's. Negative 10 radical 2's. All right, again, we have 7 radical 6 plus 4 radical 24. And there are problems you might have to simplify both radicals. Okay, but right now this one looks good. I know I can't simplify this because when I look at 6, it's just 2 times 3. There aren't any perfect squares in there, so I know I can't simplify it. So that is very good. So that one is simplified. 24, we're going to change that. It becomes the square root of 4 times the square root of 6. What is the square root of 4? 2. So radical 24 changes into 2 radical 6. But don't forget about the 4 in front. This said 4 times that radical. So we want to do 4 times the 2 radical 6. And that's going to give us 4 times 2 is 8 radical 6. Bring this guy down. So 7 radical 6's plus 8 radical 6's is 15 radical 6's. All right. So again, we're looking for like radicals, and you might have to simplify one of the radicals or possibly both of them. Let's do one more thing. Again, this is stuff you should have done in Algebra 1. So that's why we're kind of combining a lot of operations here, because this should be review. All right, simplify the expression. So just like when we multiplied, we can also divide radicals. So if I have a giant radical, I can break it apart into 2 smaller radicals. Just like if I had 2 radical numbers, I can multiply them together to get 1 large radical number. So we have the square root of 16 25ths. So what I get to do is I get to break that apart into the square root of 16 over the square root of 25. And then, can I simplify? What is the square root of 16? Well, that's one of my perfect squares. The square root of 16 is 4. So again, going back to our chart on the first slide, really important you have this. If you didn't copy it down, you should. There's our perfect square. There's our root, that base of 4. All right. So the square root of 16 equals 4. The square root of 25 equals 5. The square root of 36 equals 6. Really important that you understand that. And here, the square root of 25 is 5. This is simplified. We're done. That was easy. All right, let's look at B. Again, we have a giant radical. We get to split that up into 2 little radicals. All right. And then now we need to simplify. I'm not done. All right, so don't forget to simplify. Let's look. Square root of 12. That is not a perfect square number, but it contains a perfect square number. So this is the square root of 4 times the square root of 3. So radical 12 we can break apart into the square root of 4 times the square root of 3. And then what is the square root of 4? That is a perfect square, and the root is 2. So that turns into 2 radical 3. What is the square root of 49? That is a perfect square. And the square root of 49 is 7. So we get 2 radical 3 divided by 7. All right. Here, again, interesting fraction. We're going to split it apart. So we get radical 25 divided by radical 3. Ooh, this is different. I can simplify here. Radical 25 is a perfect square. 5 times 5. And so the root is just 5. However, I can't do anything with 3. It's a prime number. It's 3 times 1. That's prime. The only factors are itself and 1. So this is a prime number. And it is an issue for us because mathematical convention says that we cannot have a radical in the denominator. Cannot leave a radical in the denominator. Okay. That is very important. It's a skill that we really need to use to learn. It's super important. We're not allowed to leave a radical in the denominator, mostly because of before there were calculators. Trying to figure out this fraction was an issue, and it's easier if that radical is in the numerator. Now, it turns out you can calculate this by hand. It's a crazy process, very similar to long division. And you can get a decimal approximation, but then dividing those is really, really hard. So we like the radicals in the denominator. So what we need to do is a method called rationalizing. rationalize, rationalize. That's what it's called, rationalize. And so we're going to rationalize, and the way we're going to do that is simply we're going to multiply top and bottom by our radical. We're going to multiply by radical 3 over radical 3. Now, what we're doing is we're multiplying by essentially radical 3 over radical 3 reduces to 1. How many times does radical 3 go into itself? 1 time. So what we're doing is we're actually multiplying by the equivalent of 1. And so it doesn't change the value of what we're starting with. It's simply a way to manipulate the numbers. That doesn't change anything. So it's very, very cool. And multiplying by 1 is a skill that we use all the time, or turning things into 1. All right, so now we can multiply straight across here because that's how we multiply fractions, just straight across. 5 times radical 3 is 5 radical 3. And then radical 3 times radical 3, well, those numbers multiply together and become radical 9. Well, and then that radical 9 is a perfect square. What is the square root of 9? 3. So we get 5 radical 3 over 3 as our simplified, fully simplified answer. A lot of students ask, can we reduce the 3's? That's a good question. And if this had been an 8 here, then we could have reduced the 2 and the 8. We cannot reduce these 3's because one is totally radical and one is a regular Joe, and they don't mix. So you can't reduce the radical with a regular number. If the 5 were a friendlier number, we could reduce the 5 and the 3, possibly. If it were a 6 and a 3, we could reduce the regular numbers. Okay, so rationalizing is a skill that we need. We can't leave a radical in the denominator, so we must rationalize. All right, let's try one more of those. I'm going to break this up into radical 2 divided by radical 11. And again, both of these numbers are prime. I'm going to write that down. They're both prime numbers, okay? Means I cannot simplify these radicals. It's really important, okay? And I cannot have a radical in the denominator. Radicals in the numerator, totally fine. No radicals here. All right, so we need to, again, rationalize. And so I'm going to multiply by radical 11. I want to get rid of that radical in the denominator, so I multiply by it. Top and bottom, we're going to multiply by radical 11. And then just multiply straight across. Radical 2 times radical 11 is radical 22. And then radical 11 times radical 11 is radical 121, which is a perfect square. And the square root of 121 goes back to 11. So we get radical 22 over 11. Can we reduce the 22 and the 11? No, we cannot, because again, that radical 22 is totally radical and 11 is a regular Joe. Doesn't mix. You'll notice radical 11 times radical 11 just becomes 11. Radical 3 times radical 3 just becomes 3. Kind of a nice shortcut, okay? So pay attention to all of these perfect square numbers, and you really want to be able to do this well. So know these perfect square numbers, and most of your work is adding and subtracting. So make sure you simplify and then use like radicals. So have fun, and I'll see you soon.